And on we go into section 7.6, where we learn more and more identities to do with trigonometric functions. The ones in this section are called double and half angle formulas for reasons that will become quite obvious soon. And the objectives of this section are really quite straightforward. Use them and learn about them. So here are what are called the double angle formulas. Now they're called the double angle formulas because on the right-hand side, the angle in all of these functions is the angle theta, but on the left-hand side, the angle is twice as much. It is 2 theta. So what these identities do is they relate trig functions of one angle, theta, to trig functions of an angle twice as large, 2 theta. Okay. Now, they come from the sum formulas that we already had in the previous section. So for example, instead of calling, we'll just do this first one here. Instead of looking at the sine of 2 theta, what if I call it the sine of theta plus theta? Now, this is just going to use the sum formula for sine, assuming both of the angles are equal. So I end up with cosine of the first angle, sine of the second angle, plus cosine of the second angle, sine of the first angle, but they're all just thetas, and we just have 2 times the cosine of theta times the sine of theta, which is exactly what we have over here. And similarly, if we take the cosine of theta plus theta, we get cosine of the first angle, cosine of the second angle, minus sine of the first angle, sine of the second angle, and that's exactly what we have right here. And then how do I get the other 2? We're just going to take this second line here, and up at the top, if we just use Pythagorean identities, for example, cos squared theta is 1 minus sine squared theta. So if I replace cos squared with 1 minus sine squared in line number 2, we'll end up with line number 3. Okay, we replace the cosine squared with 1 minus sine squared, and now I have 2 sine squareds there. But if I replaced the sine squared in theta in line number 2 with a 1 minus cos squared theta, we would end up with line number 4. So these last 3 are all basically the same. They all come from line number 2, just with a Pythagorean identity applied to it. So I'll clear off my pen marks to clear it up. But here are your double angle formulas. So we can use these formulas to find exact values of more trig functions of more angles. So suppose the sine of theta is 5/6. Find the exact value of the sine of 2 theta and the cosine of 2 theta. So we know the sine of theta is 5/6. Now notice, in those identities from the previous page, I'm going to briefly go back so we can look at them. So in these identities, if you want to find the sine or cosine of an angle twice as big, you may need to know both the sine and cosine of the angle theta. So going back to this first example, since we know the sine of theta and we're trying to find the sine of 2 theta, so the double angle formula would tell me this is 2 times the sine of theta cos of theta. I know the sine of theta is 5/6, which means we need to find the cosine of theta, and this is now a chapter 6 problem. Okay, if the sine of theta is 5/6 and theta is in the second quadrant, find the cosine of theta. Great. Similarly for part B, okay, we have 3 options. We could do, for example, cos squared of theta minus sine squared of theta. Now, since we will end up finding the cosine of theta in part A, this is fine. Okay, we'll already have that there. But we could also do, for example, 1 minus 2 sine squared theta. This was another version of the double angle formula for cosine. And notice we already have sine theta, so we can jump right to this computation. Okay, so let's just see how the book does. Sorry about that. I dropped my microphone. Okay, so let me just clear my pen marks out of the way. Okay, so the first, for part A, we're going to use the double angle formula for sine. So that's 2 sine theta cos theta. So we got to find cos theta. We're just going to use a Pythagorean identity. The book really likes these non-unit circle approaches. That's fine. So since the sine of theta was 5/6, we have a height of 5 and a radius of 6. And we're back in the second, so I know the x-coordinate is negative. Pythagorean theorem gives us that that should now be negative root 11, so the cosine of theta is negative root 11 over 6. Now that we know the cosine of theta, we can apply the double angle formula. the sine of 2 theta is 2 sine theta cos theta. We know sine of theta is 5/6 and cosine theta is negative 11/6, and we simplify all this down to just get minus 5 root 11 over 18. Part A, done. Great. So for the double angle formula for cosine, as I remarked on the slide back there, there is a version that only involves the sine of theta, so let's just use that one. So using 5/6 for sine of theta, this simplifies down to just being negative 7 over 18. Okay, now we did end up finding the cosine of theta for part A, so you could have used one of the other formulas as well. And just for the sake of argument, suppose we did instead cos squared theta minus sine squared theta. Now the cosine of theta we found in part A is negative root 11 over 6, which I have to square. Then I have to subtract sine squared theta, which is 5/6. And I end up with 11 over 36 minus 25 over 36, which gives me negative 14 over 36, aka negative 7 over 18. Same thing. Okay, so we've got these new identities. They are not really new. They're just the sum formulas for sine and cosine in the specific case where the two angles happen to be equal. So instead of sine of alpha plus beta, we just call it sine or cosine of theta plus theta, and now we get the formulas for sine or cosine of 2 theta. So can I use these to develop, say, a formula for the tangent of 2 theta? What about the sine of 3 theta? So for tangent, we're going to do the same trick. We're just going to let both angles equal theta. And then I can use the sum formula for tangent, but using thetas in place of alpha and beta. And now notice that my numerator becomes 2 tangent of theta, and the denominator is 1 minus tangent of squared. Sorry, 1 minus tangent of theta squared. So here is a generic looking formula for a double angle formula for tangent. Okay. For part B, this one's a little trickier. Develop a formula for the sine of 3 theta. Because your first impulse might be, let's call it the sine of theta plus theta plus theta. Unfortunately, we don't have a sum formula for sine that has 3 arguments to it. So instead, start off by saying this is the sine of 2 theta plus theta, and then see what happens. So honestly, pause here, use the sum formula for sine on sine of 2 theta plus theta. You're going to get a sine of 2 theta and a cos of 2 theta, and then you can use identities, the double angle formulas from there. So pause here, try to get something, and we'll see if you get the same thing the book does. Okay, so moving on. So we're going to write 3 theta as 2 theta plus theta. Then I can use the sum formula for sine, so sine of the first angle cos of the second plus cos of the first angle sine of the second. Now we use the double angle formulas for each of sine of 2 theta and cos of 2 theta. So we had several choices for a double angle formula for cosine. With no immediate clue as to which one's going to be nicest, we'll just use the first one. Okay, there's only one choice for the double angle formula for sine. Okay, so we replaced sine of 2 theta with 2 sine theta cos theta. We replaced cos of 2 theta with cos squared theta minus sine theta. Now we just have to distribute everything out. And one thing to observe is that we have 2 sine theta cos theta squared from here. But then when I multiply this out, we're going to get another sine theta cos theta squared. Okay. All right, so here is a possible formula for a sine of 3 theta. I wouldn't say this is a formula worth like writing down or memorizing by any means. And in fact, the other ones you definitely don't have to memorize. Remember, you get to use formula sheets because the point is not to memorize stuff. But you can deduce formulas for sine of 3 theta, cos of 5 theta. You would just have to use the sum formula over and over and over again, but you could do it. Okay, so that's going to be it for this video. A quick little introduction to the double angle formulas for sine and cosine, which we then use to derive a double angle formula for tangent. In the next video, we're going to come in and we're going to learn more associated formulas.